Bismillahirrahmanirrahim. In this lecture, we are going to talk about the conservation of probability. In quantum mechanics, probability can be expressed by psi bra and psi ket. When we multiply this psi bra and psi ket, then we attain the probability. Here, in this Dirac notation for probability is equal to the integral psi rt mod square into d cube r. This is a volume, and this probability is independent of time. And when the psi mod square is equal to 1, it means probability will be 1, or function will be normalized, wave function will be normalized. Now if we differentiate of this equation, after taking the derivative, first we take the derivative of this psi t bra, and then we take the derivative of psi t ket. Then if you remember the equation, Schrödinger wave equation, time dependent Schrödinger wave equation, then we have iota h bar d over dt psi t ket is equal to h psi t ket, and it can be written as in this form: d over dt psi t ket is equal to the minus iota over h bar h. This h is for the Hamiltonian. This is the Hamiltonian, which represents the total energy of the system. And h bar is here for the Dirac constant, and psi t ket is representing the state of the system. Similarly, we take the derivative of this psi t bra. Then we have just replace this minus iota by iota and this h by h dagger. Then we have this expression. You can use both 3.76 and 3.77 into this equation. After using these equations, we get this expression. We just taking this value common in both and it is used in both terms, so we can take outside, and net change in probability is equal to the 0. What it means? The probability is independent of time. Probability is conserved. Probability does not depend on time. Probability does not evolve in time. Now we are starting again the time dependent Schrödinger wave equation, that is iota h bar partial psi r t over partial t is equal to the minus h bar square over 2m del square psi r t plus v r t psi r t, and its complex conjugate, we are taking its complex conjugate star and then star. Its complex conjugate, we are just taking the star of this wave function. Now we are just using 3.79 and 3.80, multiply by psi star rt to this equation, and multiply this equation by psi rt, and then just subtract the two resulting equation. We have this equation. Here you can see this is psi star into psi. This is according to the definition of probability, and therefore we can write here rho density, and we just arrange, we divide iota h bar here, and then j is just equal to the iota h bar over 2m psi del psi star minus psi del psi. This is j. This is the probability density. This is called the probability density, and this is the current density. Rho is called the probability density, and capital J is here for the probability current density. If you remember this term J, you have already studied in the electricity and magnetism, where J is the current per unit area, the current density. This is the same terminology here. Now, this equation is called the equation of continuity. It means probability is changing with respect to time. Then we have this factor. It means divergence of current density, and sum of both change in probability plus divergence of current density, the sum is equal to the 0. Here, this current density, when used with this del dot divergence, this is also called the particle density flux. If you remember, the flux is equal to del dot E in electricity and magnetics. Now the density operator can be defined into just the psi d ket and psi d bra. Multiplication of these is equal to this one. This is at any time t, and here we are using the some operator. This is just like the when we multiply each u operator into u dagger operator. As you remember in the last lectures, we say this is the linear operator, and then we say that if the time is not changed, then this is a unity operator, and then we also, if time is not changing, we say that this is identity operator. If the product of these both is equal to the some identity, is also called the unity operator. Now the density operator can be defined in this form.